plenary session this afternoon. We'll start with a few housekeeping remarks, particularly aimed at people who weren't here this morning. The main thing I want to remark on is this evening, after today's plenary, after today's sessions, we will have the conference gala at 7. It'll actually start, the reception will start at 7:15, and then the program will start at 7:30, and that's at the Knight Center, and for those active using the app. And with that, I'm going to turn the proceedings over to our distinguished introducer, Dr. T.R. Hughes.
Thank you very much. Welcome, everyone. I'm Tom Hughes from the University of Texas at Austin. It's my privilege and pleasure to introduce the G.I. Taylor medalist for his plenary lecture. And that's Dr. Arif Masud, who is from the University of Illinois at Urbana-Champaign, where he is professor of engineering mechanics in the departments of civil and environmental engineering and the Department of Aerospace Engineering. Arif got his bachelor's degree in civil engineering from the University of Engineering and Technology in Lahore, Pakistan, and then an MS degree from Stanford University and a PhD in computational mechanics in 1993. And that's where I know him from because I was his PhD advisor. Arif's research concerns computational mechanics, finite element methods, and in particular, the combination of engineering methods from a mathematical point of view. These are coupled in the design and the analysis of rigorous methods that are numerically robust, simple, and have broad applications. Arif has been the past chair of the Fluid Mechanics Committee of ASME and the Computational Mechanics Committee of ASCE. He's a fellow of the United States Association of Computational Mechanics, the International Association of Computational Mechanics, the American Academy of Mechanics, ASME, and the Engineering Mechanics Institute of ASCE. So with that, I'd like to introduce Arif and give him a welcome to this
Thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. It's a real honor for me to be here today to give the G.I. Taylor lecture, for which I thank the Society of Engineering Science. The topic of my talk today is a new class of variational multi-scale methods of fluid mechanics, and I'm going to present ideas in the context of flow problems with dominant interfacial phenomena, embedded constraints, and weak and strong discontinuities. Taylor lecture at SES meeting is also a platform to commemorate the seminal contributions of G.I. Taylor to the field of mechanics. Taylor is most known for his works in fluid mechanics, and there is a long list of important contributions that are attributed to his name. I've listed some of them here. These works have appeared in 3 bound volumes. 2 volumes are dedicated to Taylor's work on fluid mechanics. And I want to point out there's one volume which contains more than 40 papers and is comprised of his work in the area of solid mechanics. George Batchelor, who was a former student of G.I. Taylor, a long-time collaborator and co-worker, he wrote in the biography, The Life and Legacy of G.I. Taylor. He writes, Taylor's work is of greatest importance to the mechanics of fluids and solids and to their application in meteorology, oceanography, aeronautics, hydraulics, metal physics, and his research in fluid mechanics in particular has given the subject much of its present character. So in light of these comments, when we look at this list, here we realize that Taylor carefully selected the harder problems in fluid mechanics and using mathematical methods and experimental methods described its phenomena. Now looking at it from the perspective of modern engineering design, where all these phenomena appear in intricate fashion, integrated fashion, that is the space where computational fluid mechanics comes in. And it provides us an avenue to further explore the intricate physics that appears when these phenomena are intricately coupled. And if you look at it, Rayleigh-Taylor instability, Sampson-Taylor instability, these are interfacial instabilities. And I see a lot of symposia in this conference that are talking about interfaces, interfacial mechanics. And then there's Taylor green vortex, Taylor decaying vortices, microspins. These are internal dissipative mechanisms in fluid mechanics. So today, I will pick some of these items from this list: Rayleigh-Taylor instability, Taylor green vortex, Taylor decaying vortices, to assess the numerical method that I'm going to present. So in today's modern fluid mechanics, these investigations, fundamental investigations, become the guiding tools, the building blocks for developing a robust method for a mathematical method for developing numerical techniques. This slide shows various classes of flow mechanics problems. One could be interested in mixing flows of immiscible fluids, as shown here in the context of Rayleigh-Taylor instability, where a lighter fluid is accelerated in an ideal fluid. Or we could be interested in understanding dissipative phenomena through the Taylor green vortex. Then there are flows around submerged structures, as flow around the cylinder, giving rise to vortices that burst into turbulence. And this problem is of relevance in energy harvesting. We would be interested in ball bounded flows, bounded layers, where bounded layers separate, reattach, grow into turbulence, and regime, and we are interested to figure out the effects of bounded layer regimes. Flow will be coming on smooth orbital structure, as you see here oscillating, and waves rise to turbulent phenomena. We'll be interested in figuring out the aerodynamic or hydrodynamic stability of the structure. Then there are flow problems where we have compressible and incompressible flows, as shown here in the case of breaking waves and breaking structures. And yet, there is another class of problems, fluid structure interaction problems, where structures and fluids come together in a coherent fashion. And I've shown here in the context of confined flows, where this is blood artery interaction, where the blood, which is a more involved fluid, because it shows viscoelastic and shear independent response, is coupled with the arterioles. So if we are interested in these classes of problems, then the question arises, what should be the mathematical constructs of the underlying numerical method that can address the common issues in this wide class of problems, in addition to addressing the domain-specific issues? And secondly, what can one say about the stability and convergence of these methods in the terminology regime? So today I would like to address some of these issues in my talk, using these example problems as the motivation and also the driving mechanism for developing the method. So the emphasis of my talk is going to be on method development. So here is an outline of what I present. I first present the general underlying ideas behind variational mathematical methods for coupled field problems, and then I'm going to embed in it the ideas from this continuous development method to give rise to what I say VMDG or variational mathematical discontinuous development class of methods. We have developed these ideas in the context of a coupled field problem of Stokes-Darcy system. And this problem is very interesting in its own right because there is tremendous application in computational medicine, targeted drug delivery. It's also important for post media flows, petroleum engineering, and also appears in different forms in the new field of additive manufacturing. So we'll use this problem as a mechanism, as a driving force to develop the method. Then I extend these ideas to multi-phase flows where we have compressible and incompressible viscous sequentials. We'll have these eight interfaces, and modeling of the interfaces becomes a major issue in this class of problems. I further extend these ideas that we are talking about multi-states, so can be taken all the way to model turbulence, and I'll show that through this perspective we can variationally derive models for larger simulation. And finally, I thought to round off my talk with some concluding remarks. This slide presents the variational mathematical method, but before I go into the details of this method, I would like to express my profound thanks and gratitude to my advisor, Professor Tom Hughes, is sitting here, for first taking me as a research group at Stanford when I was a grad student, and then teaching me the beauty in the rigor of numerical methods. Stabilized methods and variation multi-scale methods, they both originated at Stanford under the guidance of Professor Hughes. And this afternoon, Professor Hughes is giving a keynote lecture on the origins of these methods. There was another thing that happened during my formative years. Hughes' Litchfield short course was world renowned for its state-of-the-art presentation of nonlinear mechanics. And in the early days, it was offered in Palo Alto at Stanford. And I had the privilege to serve as a course assistant on that course for 4 years. And it was an amazing opportunity. It introduced me to the broad field of computational solid and fluid mechanics, and that pretty much also defined the future path of my research career that I took. So really obliged for having those opportunities. So let's take a look at the variation multi-scale method, and let's take a look at it through a model problem. L is the differential operator, this is the unknown field, and that is the source field, source function. And in the context of present discussion in Navier-Stokes equations, L will be the operators in Navier-Stokes equations use the vector of unknown velocity and pressure field, and we define appropriate phasor functions for the unknown fields and corresponding weighting function, multiply, and relate it over to the weight, and this is the basis of the Dirichlet method. At this point, we make a mesh, and we try to solve the problem. And so mesh starts behaving like a filter. We are able to capture features which are larger than the size scale of the mesh, but smaller features are lost. So some part of the physics is lost. And in order to capture that part of the physics, within the Dirichlet method, the line of thought is refine the mesh. But if you follow this line of thought, we see that it's very limited in its scope, that we can very quickly exhaust any computational platform that is given to us. So the question is it possible that we can develop a numerical method that can capture both coarse scales, the mean solution, and the fluctuations, while we are still doing calculations on fluid meshes? In other words, can we develop highly accurate numerical methods? So taking that line of thought and looking at it, this is a total solution. This is what we can capture. What is lost is an error. Error is also a solution to the governing equation. So we take this additive decomposed form and we plug it in this field. For the case of, and if we are solving a nonlinear problem, then this decomposition should be looked at in the sense of projections. Whether this operator is linear or nonlinear, it is linear with respect to the weighting function slot, so we can split this likewise into coarse and fine, and we get this mixed form, multi-scale form, and where all coarse and fine scale features are fully embedded. And this becomes the point of departure from standard Dirichlet methods. Now the idea is as follows. This slot is a weighting function slot, is linear, so employing that, we can split this problem into a coarse scale problem weighted by coarse scale weighting function and a fine scale problem which is weighted by a fine scale weighting function. The beauty of variational multi-scale method lies in this fine scale problem because it provides us a mathematical zoom to go in closely and look at the finer features and provides us a mechanism to build the physics back into the system. So, in my talk, I will be putting more emphasis in the fine scale problem. And if you look at this problem, UR is the solution of the coarse mesh, so this goes to the right hand side. We see that the fine scales are in fact driven by the residuals of the Euler Lagrange equations of the coarse scale. So what coarse mesh could not solve, that is that's the portion of the solution on which fine scales are operating. So this is variationally consistent. So once we have the analytical expression for U prime, we can plug it in the coarse scale, and this is the modified formulation that we get after we put it in. The terms in the back are the Dirichlet terms. So Dirichlet method is fully preserved. And these two terms have appeared. These terms have appeared because of the assumption of the distance of fine scales. These are modeling the effects of fine scales, even though we have calculations on coarse meshes. And once we have the solution, we can go back and we can revisit the fine scale problem, and we realize that if we plug this in here, there is a natural error estimation mechanism that is built into the formulation. And that is the beauty of this particular method. So now, as I mentioned, that our objective here is to develop techniques for interfacial phenomena. So let's put an interface there. So we have this learning equation. We take our intellectual line, we cut it through. So our functions are discontinuous. Now we need to impose the continuity of the field and its flux. So flux and the field. And we can use Lagrange multiplier method to do it. Lagrange multiplier has a condition of a flux field, and most of the phenomena that have interfacial effects, they have local interfacial kinematics, which Lagrange multiplier cannot get. Penalty function cannot get. So the question is it possible that we can develop equations that will be governing the physics along this interface? And that is the line of thought that we will take. And the argument is, since we have imposed the continuity of the functions in a weak sense, so when we discretize this, then there is going to be discretization errors. So now I can use the idea that I presented on the previous slide, that we can assume a local decomposition of the solution along this interface. From a continuum sense, we can think of a form with length parameter epsilon, and one base of pilot elements, one can think of one layer of elements across this interface. And so we do this additive decomposition, and following along this line of coarse scale, fine scale problem, we can find the fine scales in terms of the residual of coarse scales along the edge, and I will show you with the help of some model problems, and we can get this formulation and it has been reported here. The terms in the black are the interior terms in the blue are the additional terms that can be derived, and these terms are common. So these terms are similar to the DG method, and there is the jump in the flux and in the field. The important point here is that the mathematical construct of the stabilization and the penalty parameter can be variationally derived without any ambiguity. And that is a major role in our mathematics that I will show. So now let's take a look at the model problem. Now let's start with the Darcy equation. As I mentioned, it's a model equation from the point of view of equation. It's a model equation for porous media flows. There's the Darcy equation, P is the velocity, F is permeability, V is viscosity, T is the pressure, and we have conservation of mass. So it's a viscous fluid permeating to a solid. That is the Darcy equation. We can develop the developing form, the standard form, by again defining the rating function of velocity and pressure, and I've written that in a concise form for presentation. We have, I worked with Professor we have derived a method that was again derived based on variational multi-scale ideas, and that provided us combination, any arbitrary combination of pressure, velocity, and information function converged. And we were able to present conservation of mass, but we were able to present it globally. In a later work, we were able to develop a discontinuous developing formulation in which we could show any arbitrary combination of velocity and pressure converges, and we could also show conservation of mass globally. So these ideas, I'm going to extend them to interfacial mechanics. So some of the fundamental ideas were developed in this work. So let's take this Darcy equation, and first let's develop a domain decomposition strategy for that. And as soon as we say their functions are discontinuous, we are not restricted to the continuity of the meshes. And so non-matching meshes comes as a byproduct of the method that I'm going to show you. So we have cut the interface, and we import the continuity of flux and the velocity field. And we do a decomposition of the solution along this interface as shown here. Gives rise to a coarse-scale problem and a fine-scale problem. And as I mentioned, our objective is to solve the fine-scale problem and extract the expression from the fine-scale velocity, which is sitting here into V1 and V2. V1 is for domain 1 and V2 is for domain 2 along this interface. And the question is it possible that we can also derive an expression from the Lagrange multiplier? And so I'm going to show how it can be done. So we take this form, we expand it out. This is domain interior terms, these are the boundary terms. We use edge functions, either functions non-zero getting edges, and then they become zero. So this localizes the problem. And we can solve this problem along these segments from both sides. And when we resolve these equations along this segment, we get segment-wise normal component of the velocity field. So we can analytically derive it. The important thing here is that these parameters are variationally derived, and we can see the operators of Darcy equation acting on the fine-scale function, couple functions that are from here. So area averaging, stress averaging, these ideas are automatically built into this mechanism. And they play an important role when we are using non-matching meshes. I will show that. Now, we have the velocity, we have analytical expression for velocity. There is no free parameter in this formulation, but the Lagrange multiplier is still appearing as an unknown. So we need another equation. For that, we can go to our continuity equation. And continuity equation had jump in velocity, velocity had coarse part and fine part. So we open the fine part of the velocity and we embedded it to the fine scale velocity field. And we can locally resolve this under certain mathematical assumptions that since we are developing a stabilized method, it allows us to use arbitrary combinations of functions. So one of them is to use discontinuous edge projection from the branch multiplier. And when we do that, we can locally resolve in the branch multiplier in terms of the average of pressures and the jump in the velocity. So now we have derived an expression for time scale velocity, an expression for the Lagrange multiplier, and the weighted parameters, again, they are fully derived through this formulation. When we plug in the force scale, this is what we get. And I just want you to take a look at these two terms. These terms are the terms that I showed you earlier. We can fully recover and derive these terms. And so this method has features, similar features as Nietzsche-like method. These are methods used in numerical techniques for coupling domains. And Nietzsche method provides the structure, but the definition or the value of the parameter is largely left undefined, and there are guidelines to derive it from obtaining this. Through this method, you can actually derive these terms, and that is the main thing, or the main thing about it. So, varying parameters are consistent, and we can imagine a domain interior stabilization for doing calculation. So now let me show you some numerical results. Here is the ice core problem with the source and the sink, and we have applied these flux conditions, balance conditions, interface conditions along this edge. It's the same mesh on both sides, again the property is the same. So here's the pressure profile, and that is what it should be. We can see any jumps in there, and pressure for the value types. Next problem what I want to show is where the actual beauty of math lies. We have this domain where the mechanical coefficients here, kappa upon mu is 1 in domain 1 and 4, and it's 0.01 into. So there is discontinuity in the mechanical properties along these lines. In addition, we are using different element types across this, and there is no problem. So this is a hard problem. This is a kind of a fastest problem of what you will find in actual field. And we will be looking at pressure along this edge, and here is what we get. The blue line and the red line is the result that we get with our method, and the black line and this green line are the results that we get with the best option for the Nietzsche method. And we see these fluctuations, and these fluctuations are coming in because they are non-matching measures, and the parameters in Nietzsche-like method, we have to select them based on certain criteria, and this criteria needs to be adjusted. And so if you pick one parameter, this is the kind of response you will get, and this situation aggravates if you embed it in a non-linear. So let me first show you the kind of problems when we are using these ideas. This chemical reactive fluids converting through solids. This is a chemical reaction, silicon carbide gives rise to silicon dioxide, which is 22% larger in volume. You can see this growth. As it takes longer distance for oxygen to get in, the rate of reaction slows down, tapers off. The solid line are the dynamical results in lots of these experiments. And we are able to capture these features. Now, as I mentioned, our objective is to be able to cover two different domains. So now let's look at the problem where we have Stokes flow and Darcy flow. So Stokes, think of it, flow over a river. So in the boundary region, Stokes flow and Darcy flow, the unknown the velocity and pressure, unknown the velocity and pressure. However, we can not combine them or couple them through brute force of gravity because the issue there is mathematical, and the issue is that the solution of Stokes lies in H1 and the solution of Darcy lies in H2. And what does it mean is that while we can impose the normal and tangential components of velocity for the Stokes flow, we can only impose the normal component of the continuity of normal component of velocity for the Darcy flow, and initial has to be kept straight. So there is a discontinuity. This discontinuity can be embedded in this framework through what we call Weaver-Joseph-Sepman condition, as shown here. We can embed these equations. So these are the Stokes equations, which are going in the top, Darcy actually is now. So we can couple them together through the branch multiplier, and the line of action is going to be the same. Solve it locally, extract the expression from fine scales, extract the expression from the branch multiplier. And when we do that, this is what we do. I like you to focus on this term, interface term. This interface term has similar structure as I showed you before. And what's important here is the stabilization terms, the definition of parameters here. And these definitions, on one side, these are compulsory definitions. Because jump in stress has a component that is coming from Darcy and another component that is coming from Stokes. And likewise, the average values coming from Darcy and Stokes, and these parameters are coming from the domain interior equations. And we can explicitly derive this. So there is again no user-defined parameter. Everything is mathematically derived. And these ideas can be used for studio-based manufacturing and targeted productivity. So now let's look at the numerical results. It's a channel flow, stores on top, cards on bottom. This is the real interface. We apply our interface conditions. For this problem, exact solution exists and provides some mechanism to look at the variational properties of our matrix. So here's a mesh that we have created intentionally, no node-on-node contact. This is a real interface, this is an artificial interface. All the stores, we do a rate of convergence. We get optimal convergence rate for the velocities here, and slightly less optimal for the differentials. Likewise for the Darcy, we are getting optimal convergence rates here for the velocity, and slightly suboptimal for the pressure. We see very short convergence for these problems. Now that we have in hand, we can now look at this distorted case, and we can see that we can capture the pressure versus stress. There is a discontinuous process interface. Normal component of velocity is continuous, and the tangential component of velocity has discontinuity. So we can capture these discontinuities for cases where we have non-matching meshes. And again, rate of convergence for that. So with this in hand, the next question becomes, does this method work only when you have equal number of unknowns on both sides? An example that I've given you, that suppose you want to model weather on Missouri. So Navier-Stokes equations can give you mean flow features, let's say, over the continent, and over Missouri, you will need to have local weather models. And local weather models will come with more features. They will have temperature, they will have humidity. So number of unknowns is going to be more. Question is, can this method be extended to solve that class of problems? And for that, let's look at problems where we have unequal number of unknowns. And what we do is our problem class is composed of displacement form of elasticity, and this form of elasticity is something that we see in our symposia here in Scotland, where people are looking at interfacial mechanics and elasticity slips and all those phenomena. So I'm going to use this as an example problem. I'm using it to show that the method that I'm presenting is not restricted to fluid mechanics, rather it can be applied to solid mechanics as well. So we have this displacement form, mixed form of elasticity provides the most flexibility in terms of developing our constituent bodies. But it comes at a price. Price is that the number of unknowns, we have a pressure unknown here, and on the other side we have only the displacement. We can develop the deep form. This is coming from the displacement form of elasticity, mixed form of elasticity, interfacial mechanics. Interfacial mechanics is again going to be developed through the formations, through the idea that it's presented. So we do our scale separation, and then we localize it and extract the expressions. So now, one fine scale is coming from a displacement form, the other is coming from a mixed form, and here's the fine scale models. We see that U1, which is coming from the displacement form, has boundary operator, which is related to domain interior operator, where constituent model is fully embedded in. So physics is all fully preserved at the interface. And likewise, for the mixed field problem, this operator is related to domain interior operator, and this is a function model for the mixed field problem. So physics is fully preserved in all of these. So now let's take a look at some test cases. And whenever we develop a new method, the first question is, do we have example problem for which exact solution exists? Because then we can talk about mathematical properties. And if we do not find an exact solution, then we look at experimental data to see if we can recover the results. Here's a cantilever beam under. This is a simply supported beam under body loads. We have an exact solution. This is the mesh for which I'm going to show you results. We have 9 node quartz, 4 node quartz, no node match here. Mixed form of elasticity, displacement form of elasticity, and for Q4, Q9, the rate of convergence is dictated by law of prevalence, and for Q4 it should be L to norm should be 2, and here is the line, L to norm of 2, and H1 is 1 or less. We have done all different combinations in here, and quadratic triangles, 6 node triangles and 9 node quartz, so rate of convergence should be 3, and H1 should be 2, and we are getting that convergence rate. So the question now, we have a method that works for different degrees. It works different degrees of freedom across the interface, works for fluid mechanics, works for solid mechanics. What can we say about the quality of solution? And for that, let's look at the residual-based estimator and revisit the analytical composition of the solution which we first found. We have a method with the embedded terms in there, so we have a better solution, but nevertheless we are solving the fine scale problem and the coarse scale problem numerically. So there is going to be some error. So any difference with the exact solution is going to be the error. Error will have two parts, local error and global error. Local error means How good was my approximation that I did to resolve my fine scales? For example, if I was applying using bubble function, how good was that bubble function? And local error means that if we use, as I mentioned, that let's use the idea of bubbles over the elements, localize the problem, and it's easy to extract the analytic terms. However, we assume that the fine scales become zero on different values, so that error exists. How can we quantify those errors? Local error can be quickly evaluated by just going to the fine scale term, plugging it back, and you get the local distribution of error. For local error, we visit our solution. UH and VH are the solution that we use. When we plug that in our variational equation, these knock out the source terms subject to which we got the solution. And what we are left with are the blue and the red terms. Red terms are just evaluated. So we make the new right-hand side vector. So we plug it in here. The terms that we know, those terms go to the right-hand side. So we have a new right-hand side vector. With the same factorized left-hand side, once we solve the problem, we get the global solution error. This error estimator is fully embedded in this class of problems. So I'll show you some numerical results again. Q4, Q9. This is a standard error where we have computed the error with respect to the exact solution. This is the distribution of error using the local error estimator, and you can see the qualitatively is able to capture that. Here is the rate of convergence for standard error. Standard error means that we are comparing with respect to the exact solution, and local explicit means that we are solving the residual and calculating that. So there is this feature of error estimation or quantification of error of the quality of solution built into the method. This is H1, Q4, Q9, rate of convergence in H1 should be 1, and here is H1 for T6, Q9, rate of convergence should be 2. So we are uniformly able to see that for different element types and classes. Now let's see, this works for smooth problems as it works for non-smooth problems. And here is an example. There is similarity, pressure similarity. The rate of convergence is dictated by the regularity of the solution. And for this problem, for global rate of convergence, it is given by 0.5 or 5, and we get that rate of convergence from the elements, both H and H1. So far, I was talking about linear problems. Reason, because we can quantify, we have exact solution, we can compare. Most interesting phenomena in fluid mechanics lie in the non-linear regime, where the interfaces may not be coincident with the element mesh lines. Discontinuities may traverse the domain, and that brings me to this multi-phase Navier-Stokes equation problem. And so let's look at the domain. This is an interface that is going to traverse on one side we have compressible Navier-Stokes equations, on the other side we have incompressible Navier-Stokes equations. The mechanical material properties, density and viscosity are going to be different. And for the compressible Navier-Stokes equations, we need to express density in terms of pressure. So this is an equation of state that is going to be operational in this zone and not in that incompressible zone. So we have density discontinuity, we have viscosity discontinuity, as well as equation of state. And these phenomena, where we have multi-phase flows, invariably come in with interfacial surface tension that gives rise to jumps in the pressure field. So we embed all of that in our beam form, and the idea is, can we now derive these expressions? So we have this fantastic decomposition of the velocity, embed that in this zone, and now since this zone is going to move across, so we have to take our line of thought to a higher level. We are going to embed this discontinuity inside the functions that represent the fine scale stabilization. So we enrich these functions through a discontinuity, compose them. These are the functions, enriched functions. And now when we solve the fine scale problem, we linearize it, we extract the expression. When we expand that in terms of these enriched functions, we see that the fine scales have discontinuity embedded. They have directionality of discontinuity embedded. And also the jump in the surface tension, any error in there, is also complicated. So this enrichment in surface tension is traversed by discontinuity, and wherever discontinuity has moved on, psi becomes equal to 1, it goes to integral stabilization. I want to point out at this point in solving these problems, because of interfacial instability, we have to add certain terms which are called those antimatters. We impose that, we add that at the interface. If we go through this line of thought and we represent our embed the level set, zero level set that shows us the discontinuity in the mechanical material properties, make density and viscosity a function of that, and apply variation multi-scale idea to the system, both Navier-Stokes equation and the level set equation for which we are solving for. We actually can recover the Gauss penalty method. The Gauss penalty method comes out as a stabilization method, and we can variationally show that. I'll show you something like this now. This is a case of two bubbles. There is no, you can see the surface of this, the circles, these are the bubbles, pressure is high. Here, the red line here represents the exact pressure. We are able to capture the pressure in just one element without any measurement. This is a force mesh, there is a fine mesh. For this problem, we can convergence streams. The next case is coalescence of bubbles. This is the model of bubble flow mechanics, bubbling flows, porosity models, developing porosity in processing of materials. This is the actual mesh on which we are solving this problem. This problem is typically solved through either measurement schemes with a lot of mesh refinement, in-time techniques, or local enrichment of the mesh. This is the mesh on which we solve it, and I've plotted it on 2 different times and cut this in 3 different directions, and you can see in any direction you see, you're able to capture the jump in the pressure in one element without ocean flow action. The next case is relative instability. Now we are going to take a look at that. This is an important problem. Transient mixing of immiscible fluids. The computer physics has discontinuity in the velocity gradient and the pressure gradient. And the interfacial phenomena is dictated by discontinuous density and discontinuous viscosity. And this is the problem where you have a lighter fluid accelerating in a heavier fluid, or you have a heavier fluid which is water on top of oil. So this problem is an physical instability. And in order to be able to model that, the numerical method should be stable so that you can model it all through the way as the problem, the complexity of the problem increases. So this is the vorticity, and we see that as the problem evolves, it becomes more and more involved. Here is the line along which we have plotted the results and compared with some coefficient results. I've plotted the interface evolution. As you see, this becomes more and more involved. This is a local element interval number, and there's a tremendous difference between values. And we are solving it without any mesh refinement, and the reason is the fine scales are actually capturing the physics. They're working hard for us to capture the physics on crude meshes. The mesh may have been fine for this simulation, but as the process progresses, this mesh becomes a very crude mesh for this at this stage, and the fine scale problem is able to represent the physics. The next is application of free surface flow problems, compressible, incompressible. Here is the impact force on the problem. The blue line is our results and plotted experimental data and some computer results. There is no horizontal velocity at this point. Again, decent correlation with some experimental data. Now, we talked about interfacial phenomena, constraints, discontinuities. Question is, there are constraints in the domain, and they appear in all different forms when we start talking about non-Newtonian fluids. In non-Newtonian fluids, we have a stress, a part of it because of the incompressibility, a dissipative, and an elastic stress. And if we look through the alright model, this model is used a lot for blood flow mechanics and non-Newtonian flows. Since the fluid is incompressible, so the elastic stress, so it should be every term in there should be isochoric or volume preserving for all elastic processes, which means the determinant of B should be equal to 1. And this also introduces another constitutive equation, this partial differential equation, which is hyperbolic, so we need to stabilize it. So we can use the technology that we have learned, we can use variation multi-scale method to stabilize it. But what I want to point out here is that enforcing determinant of B equal to 1 becomes an important internal constraint to maintain physics, to consistency of this particular term. And that can be maintained if you do a split of this B field. This is now a tensor. I talked about splitting the scalar field, we talked about splitting the vector field. We can also do the same thing to a tensor field. Yes, it is going to be computationally intensive, but it can be done. And this is a matter of forms that we will get. I'm not going to the mathematical details of that and show you the numerical results. Here is the flow coming on to a channel that is constricted in here, and we're looking at S, the stress in the x direction along this line and at this point. So at this point, we look at and plot different bicycle numbers along this line, along the surface, plot different bicycle numbers. What I want to point out here is this slide here. The determinant of P for alright group model varies from 1 to 100. And because of this violation of internal constraint, numerics becomes unstable. When you go through this line of thought that I presented, you can uniformly see, you can uniformly preserve the determinant of P almost equal to 1. So fine scales is actually correcting the physics of the internal constraint. And that's how we want it. We are applying these things to problem. Our interest is applying it to interaction. It is aorta, aneurysm in aorta. And what we are looking at is targeted drug delivery to Larson model and looking at aortic dissection in patient-specific form. So these are the applications where we can apply. And because of this consistent coupling along blood-artery interface, we get a method with high stability, and that helps us in developing a monolithic fluid structure interaction capability that can take the reading of the flows in blood-artery interaction. The next point that I want to discuss before I close is that we talk about fine scales. And fine scales can do a lot for us. They can be, they can embed this in physics. We are stabilizing the system of equations. We are enforcing internal constraints. We are coupling different PDEs. We are coupling PDEs with non-matching number of unknowns. And we are applying it to fluids and to solids. So yes, it is a good framework for applying to multi-physics type of problems. But the question is, if you're talking about scales, fine scales, can they be pushed all the way to turbulence? And then beautiful papers that have been written, the papers by Professor Hughes and co-workers that illustrate this idea. And I'm going to present so we can look at it in terms of wave numbers. And given a mesh, there are features that we can resolve. And there are features that are beyond our resolution capacity, and these are infinite in number. So typical turbulence models, what they do is, they take any viscosity that is embedded in here, and that is accounting for the subject scale that we cannot account for. So the question is, can we take the line of thought that we have taken so far and design this and derive this thing? Can we derive the fine scales and embed them in here, and will it give us the model? And that is what I'm going to show here. So we do a multi-scale decomposition of velocity and pressure. Now both are time dependent. Again, I can split the problem into coarse and fine scale problem, focus on the fine scale problem, that is what I will like to focus here. And then realize that fine scale problem is as hard as the original problem because one is harder because it is infinite dimension. So what we need to do is we linearize it and we realize that it is a mixed field problem. So it's a mixed field problem, we need to do something to stabilize it so that we can derive the expressions for B prime and B prime, and we can use the notion that split the fine scales into two levels. A level in the intermediate level where we have fine scale velocity and pressure, and a level 2 of velocity field. And the idea is this will stabilize the intermediate scales and will provide an unrestricted or unconstrained model from which we can derive expressions for V1 and P1, which will be our model for turbulence. And that is what I will show you here. So we do a split of the total scales, velocity scales into coarse and fine, and there is the schematics of that. So we have velocity and pressure, we apply BMS, that gives us coarse scales and fine scales. In order to stabilize fine scales, we do a split of velocity into coarse and level 2. And this is model building. So this is scale split and model building. And I will show you that actually when you go through this model, your fine scales are aware of the coarse scales, and the coarse scales are getting all the information, missing information back. So we look at this problem in two levels. Level 2, which are the closed force scales, we expand the velocity in terms of double functions. These are higher polynomials over the element. And solving it locally, we get an expression as shown here. So level 2 fine scales are proportional to the residual of the momentum balance equation and also the residual of the intermediate. So level 2 scales are fully aware of what the previous levels were not able to model. Secondly, we have this operator acting on V1, and V1 are represented through higher order functions. So it means fine scale viscosity is also represented in there. A third important thing is that stabilization tensor, even though we are considering these to be piecewise constant, but the residual which is coming from the preceding scale is time dependent, and so we have time dependency in this parameter. And these terms are fully derived. There is no free parameter, they are fully explicitly right. Now we go to level 1 to build our model. And when we go to level 1, we realize that now since they're time dependent, we get a system of ODEs, we need a time integration scheme. The time integration scheme that we have used here is device alpha method, but you are not restricted to use only generalized alpha method, you can use a time integrator of your choice. And when we solve it, we get this terms V1 prime and V1 prime, which are the same things that when we are model. They are proportional to the residual of momentum equivalent and continuity equivalent and some additional terms which we can derive, and these are the additional terms that we have. In our numerical implementation, we have not accounted for these terms. We looked at these terms and compared it with a case where we did not account it, and there was not much difference in the accuracy for the class of problems that we have worked with. But if we go to harder problems, probably we will need to bring them in, but at least we have no terms that can be brought into the picture. So now we have the residual based Fourier model, P prime, shown here. We can embed that in our whole-scale combination, and this is what we get. The terms from that are relative terms. Again, relative is left untouched. These additional terms have appeared. These are the stabilization terms, these are cross-affection terms, fine affection terms, pressure stabilization, and dynamic effects of fine scales. And then compare it with the turbulence models. In turbulence literature, these are the cross-stress terms, which in this particular approach we have derived, and real stress term, which we have derived. So these terms are fully derived with all the parameters analytically derived. I'll show you some mathematical results. Again, we are looking at Taylor Green vortex. This is a good problem to look at this isotropic turbulence problem, and it's a good problem to look at the dissipative properties of matter. We are looking at Taylor's number of 1600, and this is a good study to look at small scale vortices under the influence of vortex stretching. Here is the history of kinetic energy as a function of time. DNS results are shown by this black line, and they've implemented it in two element types, 8-node element and 27-node element. So we not have predefined 8-node element, but so let's look at this 3-level scale split for 27-node element. This is right on top of the DNS results here. So we can see that predefining feature, even for this problem, is fully embedded. Here is the energy decay rate, and this B27 very accurately, very closely captures the results that we get from DNS. And DNS is on much advantage. Here is a statistical stationary turbulent general flow. We have constant conditions in the blue surfaces, periodic conditions in the different directions. I'm going to show you results for 10-node tetrahedra, 8-node and 27-node hexahedra using the same framework. And we'll be looking at two different levels numbers, 395 and 590. Here's the schematics of the calculations, streamlines the particles that should be instantaneous shape of the layer. Here is the mean streamlined velocity for levels number 395. Here is the DNS results on 256 cube mesh, and I'm showing the results of 32 cube. Here is the result for three level with 7 elements and 3 level with linear elements and quadratic elements. These are fluctuation actions. The next is DNS results and comparison for levels number 590. This is DNS, and again D8 and T10 elements and comparison fluctuations. The next numerical problem is non-equilibrium turbulence. Symmetric pair appears shear layers, and they transition into turbulence. So animals instability, very classical instability. And always a crowded phenomenon, but statistics of turbulence can be compared. So here is the pressure on the surface of the cylinder. This solid line and the red line and the blue line are calculations. There's a crude mesh and final mesh, both are giving accurate results. Again, for the final mesh, because of the physics being represented with the fine scale model. And we have compared it with the DNS, with the experimental data, and with the computer data. And this is the mean streamlined velocity in the region here, and very good correlation of the statistically active values. I've plotted the mean streamlined velocity in the rate is going to be flow motion. It is the mean streamlined velocity and comparison with the experimental data for 3 different locations, and these are the velocity fluctuations. So this is a qualitative comparison of the solution. The next is a flow or a crack plate adverse to the 2000s. This problem is important because of separation and reattachment, and there's a strong backflow. And if this backflow is more than 15%, then the problem becomes extremely unstable. So, statistically averaged state of bubble becomes a criteria for looking at the accuracy of the method. We look at the size and length, the angle, and compare them with the DNS results. These lines are lines where we are plotted this thing with a severe reversal and comparison with some published results. We have used paper, print evidence, and comparative evidence, same technology, same design philosophy. The last test case that I want to show is flow around the running airfoil, smooth flow comes to the airfoil, which is oscillating. So for this, we need a technique, arbitrary programming origin techniques. So disturbance model embedded in a fair-type framework, and there's 40,000 loss of condition imposed. And you see, what I want you to show is that at bottom there are some disturbances there. So there's a 4 dB angle to that. There's a bottom some disturbances appear when they stabilize. At the top, once a small disturbance appears, this 2D structure goes into 3D and then full voltage. So this is, so large structures breaking into small is an easy thing to do. But the question is, without all normal functions, can we get the small disturbances triggered that go into large? So this is a numerical proof, or a numerical manifestation of two-way coupling between core scales and fine scales in the competition. And there are no more normal functions, there are no filter functions in these calculations. Here is the lift coefficient, the drag coefficient for two different measures, two different times, and comparison with some experimental numerical data. And this comparison is on the comparative solution was on 24 million degrees of freedom, and these calculations are showing you a 3.5. This is a mean streamline velocity at two different time points, and good comparison with the experimental and numerical. So as my concluding remarks, I said, I'm trying to present the relational multi-scale framework. It's a comprehensive framework for developing advanced numerical methods. I presented it in the context of fluid mechanics. There are lots of things that we can do with the same framework in solid mechanics. And so it's a good framework, mathematical framework to develop numerical techniques for multi-physics, multi-scale problems. The fine scale, what's the beauty of the method is that fine scale formulation allows us embedding the necessary physics in the method that restores the consistency, Pascal's stability, and we can use these methods for harder problems. These methods come equipped with error estimators, and this becomes very important when we are solving problems for which we may not know the solution. So we need to quantify the error, we need to talk about the quantitative solution. I've also presented you a couple of three problems. I presented in the context of fluid mechanics as well as solid mechanics. We can use these ideas to cover different PDEs across interfaces and solve some interesting problems. These interface coupling operators, they come up. So multi-gate patching techniques in computer science is also interesting area where we match different meshes across mathematical solutions. And if you follow this line of thought, this multi-gate patching comes out automatically as a byproduct of the process. I also talked about imposing internal constraints in viscoelastic fluid. So you can impose these constraints on scalar, vector, and two fields, and you can fully derive all stabilization terms that you would need. Hierarchical application of VMS idea. And I showed you mathematically, I showed you the diagram, are concurrent and consistent two-way coupling to the equations. And I also showed you through the numerical example of this two-way coupling between fine scales and coarse scales. So we can derive these terms. We don't need to add any filter functions or any parameters in the framework. In all the problems that I've shown you, there are no user-defined parameters. I showed you different problems, and I showed you different model cases. There are no user-defined parameters in any case. You can derive everything through this approach. So the visual-based models can be derived. And my papers are at this place, and there are some simplified codes that if you get excited about VMS, you can download and you can try them out. There's a VMS method excites you. There's some excellent people sitting in the audience today, and they're working both in turbulence, in instability phenomena. There's a symposium after this lecture, and I will invite you to attend that and look at the works. What I presented and what they're going to present is what variation on that scale method, the better scale shares. So with that, I want to acknowledge all my collaborators that I learned from the idea that I used in the presentation that I created for financial sport, the computation sport from different organizations. With that, I thank you.
View of fluid mechanics from this point of view. We have time for one or two questions. Question.
One of the very compelling examples that you showed was a beautiful fluid flow channel, a fluid flow down a channel, where the fluid struck a barrier and then droplets formed. With your methods, is there ever a convergence, an absolute solution for the way these droplets form, or is that somewhat stochastic?
Which problem?
This is fluid flow down a channel, it struck a barrier,
Yes.
and then some droplets formed there. Do you ever converge on a single droplet pattern, or is that somewhat stochastic?
So answer to your question is, we can do a mesh alignment study and take a look at and are we recovering that thing? There are two things that are going on in there. There's accuracy of the physics and accuracy of the interface that is defining the flow. What you can do is, you can ensure that mass is conserved in this phenomenon. If your level set is not accurately resolved, and level set has an error, then you will be losing mass because of the representation of the interface. And that is where I said that when you apply BMS idea, do not just apply to the governing system of equations. Also apply to level set and look at fine scales as the error that you want to fix back so that you can ensure conservation of mass. So if you have conservation of mass, then the physics is preserved. And then the second question is that how fine the features are you able to preserve in the post mesh? For that we are going to mesh refinement studies and take a look at that.
Thank you.
Any other questions or comments? If not, let's thank our once again.